The overarching purpose of Unit 4 is to study special functions. We've already taken a look at rational functions. Next, we want to examine exponential and logarithmic functions. But to really understand the relationship between that pair of functions, it's important for us to do a little background work with inverse functions. So that's what we'll do here in section 4.2. Also, we have learned 4 basic operations on functions. We've learned how to add functions, f plus g, subtract, f minus g, multiply, and divide. But there's another operation that we need to learn called composition. So that's what we're going to examine in this video. Here's the definition of composition. Given 2 functions, f and g, the composite function denoted f, you can read that f circle g, you can read it f composed with g, or you can read it the composition of f with g. This is defined by f composed with g of x is equal to f of g of x. Now, before we break that composition down, it looks a little bit abstract, but make a note that this new symbol is what we call a binary operator. Binary because it has an argument on either side. That symbol represents a way of combining f and g. Now, you already know 4 binary operators. You know plus, minus, multiply, and divide. Each one of those symbols represents a particular way of combining the 2 functions. You know there's a difference between f plus g and f minus g. So when I see this composition symbol, it represents a way of combining f and g. In particular, we're going to evaluate f of g of x. That is, we're going to evaluate a function of a function. Let's give this a try on example 1. Let f of x equal 2x squared minus 5 and g of x equals 3x minus 7. So f is a quadratic function and g is a linear function. And we want to find each of the following. First of all, f composed with g of 3. So here's the pattern for expanding a composition. What we have over here on the left side is going to be expanded according to this rule. So the difference here is that my argument is equal to 3. So I'm going to take the leftmost function as the outside function, and the right function, or the function on the right side of that operator, g, as the inside function. And the argument is going to be 3. So embedded inside the function f is g of 3. So we're going to start on the inside and work our way out. So for now, we're going to postpone evaluating g and just copy it down on the next step. Working inside parentheses here, we need to evaluate g of 3. Now, we know what that means. That's just function notation. G of 3 simply means we're going to go to the function called g and plug 3 in for x. So we're going to evaluate 3 times 3 minus 7 inside parentheses here. 3 times 3 is 9, and 9 minus 7 is 2. So after evaluating g of 3, we ended up with 2. And if you look at the resulting expression, we now need to evaluate f of 2. Well, we know what that means. We're going to go to the function called f, and we're going to plug 2 in for x. 2 times 2 squared minus 5. Or in line with our work here, 2 times 2 squared minus 5. Following our order of operations, beginning with exponents, 2 squared is 4, 4 times 2 is 8, and 8 minus 5 is 3. So our final answer here is 3. Now let's go back over what just happened. We started with an input. That input was 3, and we plugged it into g. After evaluating g, we had an output. The result of g of 3 was 2. Well, then we took that output and immediately plugged it into the other function f, and f gave us a new output, 3. So really, the composition of 2 functions is just evaluating 2 functions in a row. Let's try that in the opposite order on example B. We want to evaluate g of f of 3. So our outside function is g, and our inside function is f, and the argument is 3. So starting on our innermost set of parentheses here, we need to plug 3 into f, and we're just going to postpone g to the next step by writing it down on this line. Evaluating f of 3, we're going to go to the function called f, and we're going to replace the x with 3. So this becomes 2 times 3 squared minus 5. And by the way, you can put that square either inside or outside parentheses there. 3 squared is 9. 2 times 9 is 18, and 18 minus 5 is 13. So now we need to evaluate g of 13. So this time we're going to be using this function rule, and we're going to replace the argument x with 13. So we have 3 times 13 minus 7, or 39 minus 7, which gives us 32. Once again, retracing our steps, we plugged a number into f. F spit out a number 13. We took that number 13, plugged it into the other function g, and g gave us the output 32. So again, we're just evaluating two successive functions. Now, what's different about example 1 and example 2 is the argument. If you notice on example 1, we had a numerical input for the argument, but on example 2, we're going to be plugging in a variable. So we've got a variable in this spot and a variable in this spot. We've also got two new functions. So this time, f of x is the linear function 2x minus 3, and g of x is another linear function, negative 5x plus 1. So let's see what happens when we evaluate f composed with g of x. So the left function there becomes the outside function. The function on the right of the circle is the inside function. So we want to evaluate f of g of x, a function of a function. Now we're going to follow the same procedure that we did on the previous example. That is, we're going to start on the inside function and postpone f until the next step. However, there's nothing to evaluate here. We don't have anything to plug in for the argument. So we're simply going to replace g of x in this argument position with its function rule. Notice g of x is equivalent to negative 5x plus 1, so I can use that to replace that function name. So in parentheses, we're replacing g of x with the entire function negative 5x plus 1. Okay, that's round 1. Round 2, we're going to be using our function f. So this tells me come use this function, and in particular, this is the rule. So in the function rule, we have the variable. You can think of that as the argument or even a placeholder. I'm going to put a box around that x because whatever I have in parentheses here is going to land in that box. Notice what we have in parentheses here, negative 5x plus 1. So I'm going to take all of that and plug it into that box. This is going to give me 2 times the argument, negative 5x plus 1 minus 3. Notice that argument just landed in that box. Okay, so that's a function of a function. Now we simplify the function. Of course, you know we need to distribute our 2 here. So this becomes negative 10x plus 2, and we have a minus 3 out there. And simplifying, we end up with negative 10x minus 1. So if we have a variable input, notice we end up with a variable output. Whereas if we're plugging in a number, we're going to end up with a number. Let's go the other way and evaluate g composed with f of x. That is g of f of x. So starting on the inside function and postponing g, we want to replace this time f of x with its function rule. So here's f of x. Its function rule is 2x minus 3. So I'm going to take that 2x minus 3 and replace f of x in the argument. That's round 1. For round 2, we're now going to be working with the function called g. So I know we're using g this time. In parentheses, I have the argument, what I want to plug into the function g. So I'm going to look at the function rule for g, and where I see the argument or the variable, I'm going to put the argument in that position right there. So I'm going to take the 2x minus 3 and put it in that position. So we have negative 5 times 2x minus 3 plus 1. So notice the argument landed in that blue box. Okay? So we have a function evaluated at a function. Let's simplify. Distributing the negative 5, we have negative 10x plus 15 plus 1, or negative 10x plus 16. We plugged in a variable, and we got out a function of a variable. So again, evaluating a composition is either two successive functions evaluated at a number, or you're evaluating one function at another function. Order is important, and it takes a little bit of practice. So let's do one more example here. Example 3, f of x is a square root function. Square root is 7 minus x. G of x is the quadratic function, negative 4x squared plus 7. Let's begin with f composed with g of 0. Keep your functions in order. F on the outside, g on the inside. We're going to wait to evaluate the outside function until the next step. Here, we need to evaluate g of 0. So we're going to go to the function called g, and we're going to plug in a 0 for x. So we're going to put a 0 in that spot right here. This gives us negative 4 times 0 squared plus 7. Or negative 4 times 0 plus 7 gives us 7. Okay? Next, we're going to use the function called f and plug in the argument 7. So here's my function f, here's the function rule. I'm going to put 7 in for x. So this gives us square root of 7 minus 7, or 0. So first we evaluated g of 0. We got the output 7. We plugged 7 into f of x, and we got out 0. Working our way down to example B, we have g composed with f of negative 2. This is g of f of negative 2. Hopefully you're getting the routine down. We copy down our first function or our outside function, then we evaluate the inside function. F of negative 2 is the square root of 7 minus x, or 7 minus negative 2. So there again, I'm just plugging in the argument negative 2 for x. So this gives us g of, and in our radicand here, we have 7 plus 2, or 9, and the square root of 9 is 3. Then we evaluate g of 3. So I go to the other function, plug 3 in for x. We have negative 4 times 3 squared plus 7. 9 times 4 is negative 36. And negative 36 plus 7 gives me negative 29. The next two examples have a variable argument, so we should anticipate the final answer being a function of x. So we want to evaluate f composed with g of x. So we're going to start on the inside function and completely replace g of x with its function rule. So we're going to have f of negative 4x squared plus 7. Then we're going to go use the function called f, and we're going to take everything that we have in parentheses here and plug it in for the variable. So this will give us the square root of 7 minus the argument, negative 4x squared plus 7. So distributing our negative inside parentheses, we have 7 plus 4x squared minus 7. And this gives us the square root of 4x squared, which you can see is 2x. Last variety here, g composed with f of x. G is on the outside, f is on the inside. So I'm going to replace f of x with its rule, which is square root of 7 minus x. And then we're going to plug this into the function called g. So I'm looking at my function g. There's the argument or the placeholder. So my square root function is going to land right there. So we end up with negative 4 times the square root of 7 minus x squared plus 7. As you know, when we square a square root, it cancels out. So we have negative 4 times 7 minus x. Again, this canceled with this, plus 7. Distributing our negative 4, we have negative 28 plus 4x plus 7. And then combining like terms, we have 4x minus 21. Now compare example A and B. we did actually compare example C and D. We did f composed with g of x and came up with this answer. We did g composed with f, the opposite order, and got this answer. So based on that information, is composition a commutative operation? Now, what does that mean? Remember, addition is commutative. So I can add these two numbers in either order and get the same thing. Whereas subtraction is not commutative. 2 minus 3 is not the same thing as 3 minus 2. So since when I change the order of my functions in composition and I get two different answers, we would say no, composition is not commutative. That means you got to get it plugged in the right order. So this is an introduction to the composition of two functions, and we'll use this skill as we study inverse functions. So under what conditions would you need to actually execute a composition in an application? Let's consider a geometry problem here in example 4. The surface area S in square meters of a hot air balloon is given by S of R equals 4 pi r squared, where r is the radius of the balloon in meters. So our surface area is described as a function of the radius. That is 4 pi r squared. So my input here is the radius and the output is the surface area. Now, if the radius r is increasing with time in seconds, according to the formula r of t equals 5/8 t to the fourth for t greater than or equal to 0. Okay, so now we have another function, the radius as a function of time. That is 5/8 t to the fourth. And we have a restriction here, t has to be greater than or equal to 0. Remember, t represents time in seconds. So t greater than or equal to 0 just means that we're dealing with positive times. That's perfectly logical. So here we have two functions. Surface area is in terms of the radius, and radius is in terms of the time. So you can think about that radius as kind of like a middleman variable. But let's look at the problem. Find the surface area S of the balloon as a function of time. So I want to skip the middleman R. So again, surface area is a function of r is a function of time, so we should be able to write surface area as a function of time. And we can actually accomplish this using composition. So what we want to do is evaluate surface area composed with radius, and we want this to be a function of time. So we're going to break this down into an outside and an inside function. Just like we do with f of g of x, we just have different variables to deal with here. So our outside function is going to be the leftmost function, s. Our inside function is going to be r, and the argument or variable is t. So we want to evaluate s of r of t. As we've been practicing, we want to replace our inside function first. So we're going to come over here and find r of t and replace it with its function rule. R of t is equivalent to 5/8 t to the fourth. So we're going to replace r of t over here with 5/8 t to the fourth. Next, we need to evaluate s of 5/8 t to the fourth. Remember, what's in parentheses there is your argument, and we plug that in for the variable. So let's go to the function called s. Here's my function called s. The argument or variable is r. So remember, we think about that argument or variable as a placeholder. So everything that I see in parentheses over here, that is 5/8 t to the fourth, I'm going to plug in to that box right there. So I'm going to copy down all the details, 4 pi. Now, replacing the r with the new argument, which is 5/8 t to the fourth. Remember, we had an r squared, so we're going to square that. So we have 4 pi times something squared. 4 pi times our new argument squared. So now our surface area is a function of t, or time. All we need to do at this point is simplify. So first, let's execute the exponent and square everything inside parentheses. 5 squared is 25, 8 squared is 64. And remember, when you raise one power to another power, you multiply those powers. So t to the fourth squared becomes t to the eighth. Now, I see a common factor. between 4 and 64. 4 will go into 64 16 times. Now we just want to write it in a readable way. So generally what we do is start with the constants there, 25 and 16, and also recognize pi is a constant. But we generally write that on the right side just like it's a variable. And then we have t to the 8th. So that's an acceptable form of the answer, or you could also write it 25 pi t to the 8th over 16. So again, we started with surface area as a function of radius. Radius is a function of time. But now our surface area is a function of time alone. And again, we accomplish this with composition.